So to recap where we are, we've diagnosed that the motor does not run with the TechMate. We've already confirmed that we had high voltage power to the high voltage connector. So now we need to remove the control and diagnose whether the motor is also failed. Before we did that, we turned off the power and we waited 5 minutes. So the power's been off for 5 minutes. We're going to go ahead and disconnect our high volt lead. We're going to disconnect our communication lead, and we are going to remove the control, which is simply removing these two 1/4 inch hex head bolts. On the model 2.0, which hasn't been made for over 10 years, there are actually 4 bolts on the control. 2 of them are star bolts and 2 of them are 1/4 inch hex head. The star bolts, I apologize, actually hold the control inside the can. The hex head bolts are the ones that actually hold the can or the shell of the control onto the motor. So we're just going to remove those 1/4 inch bolts, and then we're going to move the control gently to a point where we can reach inside and disconnect the 3-pin connector. And I know you couldn't see that, so I'll show you. There's the connector, and there's where it goes on the control. Now, the reason we were waiting 5 minutes is inside this control, a part of what helps it turn AC to DC and back into 3-phase is these capacitors. We call them bulk capacitors. They're fairly large microfarad capacitors, and they store a lot of power. So we turned the power off to the control and waited 5 minutes so that these capacitors could discharge and we could safely work inside here. So with the TechMate, we've diagnosed that the motor does not run. We've diagnosed that this control is failed. So we're going to put that off to the side, and now we're going to diagnose whether the motor is failed or not. And really, what you have right here is a 3-phase motor. No different than any other 3-phase motor. We're basically going to check it from each lead to ground and from each lead to itself to check the ohms of the winding and to make sure that the windings themselves are not shorted to ground. So the ground check first, because that's the easiest one in my opinion. We would simply take the meter, connect it to each lead, and go to ground. Now on the 2.0 and the 2.3 motors, the end shell would be ground. On the model 3.0, the X brace would be ground. In the model 3.0, when we made the control down onto one board, the capacitors grew a little bit and we had to leave some room for them to sit up inside the motor. Really no difference in how the motor operates. So we would check each one of our leads to ground and make sure that we are reading infinity. If we read infinity on our ohm meter, and I should have mentioned probably it's good to set your ohm meter when you're checking ohms to ground to the highest possible scale. If we're reading infinity on all 3 of our leads, that one check is a good check. That motor passes that check. If any of those readings was less than infinity, really less than 100,000 ohms, then there's some continuity between the windings of the motor, which would literally be the windings of the motor and ground, and that would indicate a failed motor. No sense in even doing the second check. It's been my experience that most motors either read infinity or 0 on the meter. So if it passes this test, the next test is the phase-to-phase test. This is where we're going to check the windings themselves to make sure they are reading the proper amount of ohms. Now, all of our motors are going to read 20 ohms or less. We don't make any ECM motors 1/3 through 1 horse that read more than 20 ohms. So if you read more than 20 ohms, that's a bad motor right off the bat. The only other criteria for any 3-phase motor, including ours, is that all 3 of these readings be the same, plus or minus 10%. In other words, your meter's never going to read the same 5 ohms each time you check it. So as long as all 3 readings are the same and it's below 20 ohms, we have a good motor. So we would simply check from, and we'll just start here and call this 1, 2, 3, and it wouldn't matter if you called this 1, 2, 3. We're going to check 1 and 2, and then we're going to check 1 and 3, and then we're going to check 2 and 3. And if I read the same, plus or minus 10%, in other words, if I read, like in the example you're looking at, 5.1, 5.3, and 5.5, that's a perfectly good motor. They're not all perfectly the same, but they're within 10% of each other, and they're below 20 ohms. If any one of these readings was more than 10% off of the other, or it was over 20 ohms, we would have a bad motor. So we've diagnosed with our ohm meter that the motor is good. That means that all I have to do is replace the motor control, which you can get motor control separate from the manufacturer only on variable speed motors. That's the only ECM motor you can replace the control separate from the motor. If with our ohm meter we diagnosed that the motor was also failed, then we would have to replace the motor and the control. So let's go with replacing the motor, or the motor and control. That means I've got to take the whole motor out and put the whole motor back in. Of course, I would want to get the blower wheel centered and tighten the hub nut from the blower wheel down on the flat part of the shaft. After that, I also want to make sure that my control is oriented so that the plugs are facing down between the 4 and 8 o'clock position. This is going to make sure that if any water were to drip down on the motor, that it would run off the motor instead of running down into the plugs where it could cause damage. For the same reason, we want to make a drip loop out of our harness that goes to the motor. After we've plugged the connectors into the motor, we want to make a drip loop. So if any water got on these wires, it would also run off and drop off the wires before it could get all the way into the motor. So if we're only replacing the control, again, keep in mind that before we put the control back on, we do need to plug that 3-pin connector back into the control. So we would plug the 3-pin connector back into the control, rock the control up to the motor, put in our 2 1/4-inch hex head bolts, and we'd be ready to connect the wiring back to the motor. Of course, making sure that these connectors, as this blower section goes back into the appliance, are facing down. For example, if this happened to go in a downflow appliance, then this would be 180 degrees, and that would be the proper orientation for that control. Now, all of these controls must come from the manufacturer, controls and motors. There are no generic variable speed motors. And of course, you should read all the literature that comes with those parts as well. Let's go over the multiple generations of variable speed motors that we built over the past 20 years. The first one, the model 1.0, has not been produced for over 15 years. If you need troubleshooting help, or if you find one failed, you will have to go back to the manufacturer of that appliance for help on that motor. The model 2.0 has not been made for over 10 years. However, the 2.3 motor is backward compatible to replace 2.0 controls and motors. The current generation 2.3 motor can only be replaced by 2.3 motors and controls, and the current generation 3.0 motor can also only be replaced by 3.0 motors and controls. A good note to keep in mind, the 3.0 is not backward compatible to 2.3 motors and controls. The 3.0 motor communicates with serial communication, the 2.3 motor communicates with AC or DC communication. So 2.0, 2.3, and 3.0 motors are all available for replacement in control or motor or both from the manufacturer. And that makes it very beneficial in the field for replacing just the part that has failed. Now, it's worth noting that some manufacturers, if the motor is still under warranty, may require that you replace both the control and the motor, even if you've diagnosed that only the motor has failed. And that's perfectly fine. It's under warranty and that's their policy. But if the motor's out of warranty and you've diagnosed that the control is bad, but the motor is good, the ethical decision is to only replace the part that's failed for the customer. Remember that everything we just covered on troubleshooting variable speed motors can be found in the ECM service guide, including a motor identification chart to help you figure out which motor you're working on and get to the right section in the guide. After you've replaced any part, it's a good idea to find out, if you can, what caused that part to fail. In the case of motors, water damage can be very critical. If there's any water damage from a drain line that's leaking, a drain trap that's overflowing, or even from a evaporator coil that might have frozen, we want to make sure to solve those problems so we don't get a repeat failure. And obviously, a frozen coil could be caused by an airflow issue. Any airflow issues we want to make sure and solve, not only so that we don't fail a motor, but also because it's going to decrease the capacity, the efficiency, and the life of the system. Keeping in mind that even though this is a variable speed motor, If we have a severe enough airflow problem, we could run the motor up to its speed limit and still be tripping limits and freezing coils, having problems that we think we shouldn't have with variable speed motors, but could be very detrimental to the system. When you're finished with any service call, especially one where a part had to be replaced, it's obviously a good idea to check all of the wiring connections in the system. In the case of our motor, often the blower section will have to be pulled out, which means wires had to be disconnected and reconnected on the main circuit board. Good idea to check them and make sure they're all back in the same place. This will also get checked if you run the system in both heat and cooling to make sure that everything works properly. And I know it's not always a good idea to run the air conditioner in the middle of winter, and customers don't like the furnace running in the middle of summer, but you can turn the breaker off on the outdoor unit and just make sure everything on the inside cycles correctly, just so that you don't have that system failure when the seasons change because one little wire from the thermostat didn't get connected. I always like to check all the safeties in any system, make sure they're working, the pressure switches, the limit switches, that kind of thing. And I know we've already talked about drains, but all of the drain hoses from the air conditioning system, from any 90% furnaces, even from humidifiers, just make sure all the drains and all the traps are free and running clear. One thing that, believe it or not, will make a big difference to your customer is to return the thermostat to their setting. When you leave the home, customer has to go over there because an hour later it got too hot or got too cold and they had to turn it back. That leaves an impression in their mind. Just that one little thing can make them say, wow, that was really nice of him to do that, or even just that you asked, what should it be set back to? And I'm also, as I'm sure you are, a very big proponent of annual maintenance. Annual maintenance prevents a lot of system failures and keeps the system running at its peak efficiency, peak capacity, and we know that it makes it safer. So don't forget to offer your annual maintenance and talk to your customer about other indoor air quality products that they may not already have. A variable speed system is a high-end system. It's very likely that that customer would be interested in other indoor air quality products to make their home more comfortable and more healthy.